We talked previously about the belief in near transfer. And of course, whatever we talked about in high fidelity systems like SIMnet, like sophisticated military training simulators, they were the byproduct of this belief, the belief in high fidelity simulators or belief in near transfer. And so you remember we talked about the relationship between mental space and physical space in the near transfer, and there was also a question in the exam about that. Can any one of you just briefly describe what it is, like what is the relationship between mental and physical space according to the belief in near transfer? Yes? Yes, the mental space corresponds to the physical space. So if there are two skills in the mental space with the same distance, the same two systems or simulators in the physical space and the same distance between them exist. So the distance in these two spaces correspond to each other. If one distance increases, the other one also increases. So now we're going to talk about far transfer, which is the opposite side of this spectrum. And you remember we had like something like a Venn diagram. And I'm going to have similar thing for far transfer. Mental space and physical space. So in mental space, we have two skills. Skill number 1 and skill number 2. And in physical space, we have two systems or simulators. Their distance does not correspond to each other. So as you can see, we have two skills in the mental space. And those two skills are pretty much close or has a distance. And if you think about the same corresponding systems in the physical space, their distance in the physical space might be much more. So in other words, you might have two completely different systems that seem entirely different from each other, but your skill in dealing with those systems or in using those systems is pretty much alike or is very close in the mental space. So this correspondence between the mental and physical space is no longer valid or true in the belief in far transfer. And particularly, this exception is in the direction that in the physical space, there can be or two systems or simulators can be completely different from each other, but in mental space, they're basically the same. So imagine two tasks like playing chess and driving or something like that, that have absolutely nothing in common. But they argue there might be a lot of psychological similarities between them when we do them, so that if we learn one or develop skill in one, that skill is transferable to the other. So that's the belief. And if you compare that with the belief in near transfer, it basically does not follow that identical elements theory. So as I said, two different systems or simulators might need skills that are pretty much alike or similar. So if you remember the identical elements theory of Thorndike, Edward Thorndike, that we talked about as the essential backbone behind the belief in near transfer, can any of you say how what I just described in the belief in far transfer contradicts identical elements theory? So identical elements theory said that for two skills to be transferable to each other, those systems should have identical elements, or the level of identical elements between two systems is proportionate to the level of transfer between them. Yes? Can you repeat that, please? Yes. So basically, it is that identical elements theory is assuming that there are like specifiable elements that we can see between two tasks on the surface, or visual aspects of them. And then the level of similarity or visual similarity or surface similarity is proportionate to the transfer. But this belief in far transfer goes beyond that surface similarity and is focused more on the psychological aspects of what human does in dealing with each of those two systems. Yes?
The environment between the two should be similar. Far transfer is a notion of both person mentally that should be similar.
Yes, exactly. Yes, that's the focus is for instead of focusing on the physical or physical properties or physical aspects of the similarity of two systems, it is more focused on what human or human operator or trainer or human side, what activities humans are conducting to do each of those. So we're focusing more on the behavior side than on the system side. So it is possible, that's a possibility. It's not a condition, but it is a possibility, according to the belief in far transfer, that two tasks that do not have many common features or elements, the skill between them might be transferable. So it opens the possibility. It does not say how exactly, but it says it is possible. So as a result, the identical elements theory is no longer a necessity in far transfer. And we can just, or it kind of puts away the emphasis from the feature or elements aspects or visual aspects to the psychological aspects. So as I said, if you think about tasks as dissimilar, like playing chess and driving, might be, it's important to consider that, might be transferable to each other. So if you learn one, you might get better in the other. Now, I'm not saying they are, but there can be research on, it's just more just an example of how different two tasks can be, but the skill can be transferable between. Again, you should just remember that this is a possibility, and I'm emphasizing this might be or can instead of is. Because if you want to show that it is, you have to prove that, again, experimentally by doing experiments and showing that. And if you think about it a little more, this notion is more focused on, like, looks at human psychology or mental space as something like a muscle that you work with it in certain aspects, it gets better and it can be transferred to other things. It is not task specific, and it does not focus on certain tasks and say, well, we have to spend this much time on this task to get better only on that task. But it says that these, for example, if you think about like general education or quick K-12 education, the belief is that you practice on subjects like math, biology, memorizing words or history and certain things, and your mind gets prepared or gets kind of exercised on those things so that it creates this potential to learn other things in future. So it is also an educational assumption in our current system of education too. So it's just like something like a brain as a muscle kind of thing. Do you have any question about the belief in far transfer? Yes.
So, would this directly relate, like way back in week 4, we talked about how like anything we do in life, like impact our future skills, that kind of.
Yes, when we discussed that topic, it was mostly just to give you an idea about like how this whole science of training thinks about human skill acquisition. Like it was a very broad notion. But here we are more specific on one of these two theories, far transfer, near transfer. But you're right, if you think about it from that perspective, it is basically the same notion that it's just brain is a plastic system and you work with it and it gets better and it transfers to other tasks, even not those tasks that you worked on specifically before. Yeah, that's a good point. I mean, it's just whatever you do today, even if it's not relevant or similar on the surface to what you will do in future, it might affect that. Yeah. Chris. So, any other question? So now we're going to talk a little bit about the roots of belief in far transfer or its origins. Basically, at around 1950s and 60s, again, with the introduction of more sophisticated tools to the military, the training costs were skyrocketing at the time. And there was a need to reduce the cost of training. Of course, by that time, it became a bit clear that using high fidelity systems was pretty much effective. But the question was, it's too expensive, how we can reduce the cost, whether lower fidelity systems can have comparable training benefits to high fidelity systems. So we have, for example, a simulator for nuclear power plant. And the question was, could we have a simpler system instead of a very expensive one for training? So this made psychologists and training scientists to think about ways to do that. So if you imagine a task or working with a system, they were thinking about how to do that, how to develop effective low fidelity simulators. Now, if you want to think about like, okay, we have a task, just like what we talked about in military tasks, for example. And of course, the easiest way to train them is to create a replica or a close match or high fidelity simulation to that task to train it. Now, imagine you do not have that much budget. Imagine you only have some simple stuff around you, but your goal is to create that, use those simple stuff and create a low fidelity simulator. How do you do that? Or how do you start doing that?
You have to focus more on the task instead of the environment. So you just start completely scrapping all the environmental factors and just focus on getting the task information in there.
Okay.
And then the manual.
Yes, you start with the task and the surrounding elements. Exactly. You go to the environment of, or target environment, you see how, generally what's the goal of the task, what are the tools that are used, and you try to replicate them with whatever you have, or get as close as much as you can to those tools. Any other thought? Yes?
Research the task specifically, you can focus more on like that's about more of a
Yes, and your name? Okay, Ahmed. So, yes. You can think about like that specific task or tasks that are very similar to it, and then see whether there is an inexpensive way to practice that. It's a pretty close approximation to that real task. And that's another kind of research that you can do. Any other thought? So the goal is to create a low fidelity simulator for a task with simple things that we might. So imagine the task is, say, surgery. We don't have anything. We only have certain simple tools like pencil or some tubes and some simple stuff around us. What do you, or how do you go ahead and train those skills with these simple tools? So I would draw your attention more on the human side again, and say that one of the first things that you need to focus on is that expert or that performer is doing certain activities, is doing certain things. It is whether using with certain tools or thinking, that psychology is very important. Thinking or doing some mental activities, and you try to derive those activities as much as you can so that you can think about whether I can replicate that or whether I can copy that in a simpler environment for that psychological processes to be practiced. That focus on human side is very important. Of course, it needs to focus on the task, on the tools, on the environment, on similar tasks, but the first focus should be on that human side. And how to do that is, again, with task analysis. Finding the basic mental and physical activities and seeing if those activities can be practiced with simpler stuff. So as an example, one way would be to go to that environment and ask that expert that what are the steps that you follow, that what is it that you focus on at first, and then what's the next step, and then you document them and you try to train them with simpler materials. So one of the, on that side, we had this, early psychologists like Edward Thorndike on the side of near transfer. And in this side also we have famous psychologists, which came later. I mean, the belief in near transfer is older, but this one is more recent. Herbert Simon, famous psychologist, and he also had a Nobel Prize in economics, behavioral economics. Simon, or Shimon in Hebrew, Simon in English. And he had one, I mean, he had many ideas and a lot of new discoveries in economics and other aspects, but within this domain, he had one idea which is called problem isomorphism. And isomorphism is iso is one, morph is shape. It's like, but kind of, if you think about different problems, if there is like one shape between those problems, and I'll describe that more now. And the problem isomorphism is basically saying that seemingly different problems, or by problem here, it's basically meant skills, tasks, anything that you see in the world, which is phrased as problem, or a task. You can think about the task. Seemingly different tasks or problems can share a single underlying structure. So there is an isomorph of a problem that is represented in different shapes in the world. So if you think about different problems or different tasks, and you can derive the shared aspects between these problems or tasks, and if you can train that shared aspect, then that skill can be transferred to all of those specific tasks. So you can think about certain problems in mathematics that they all share the same underlying structure. Or you can think about route finding in driving or in a video game. They share the same underlying structure, for example. And you derive that structure, you train that, and then that skill can be transferred. And this deriving the similar aspects of different tasks, of course, is simpler, and it does not have as much detail as the original task. That's why it has to use low fidelity simulator to train it. So it's very like abstract, broad. Now I'll talk about that more later on. But if you have questions about whatever we discussed, just let me know before proceeding. So if you don't have question, it's good to give an example of what problem isomorphism is. So if you think about the troubleshooting task, finding the faulty component in an electronic or mechanical system. So we have mechanical systems on one side, and by mechanical system, we mean things like automobile or a gas turbine or heating system or most parts of a nuclear power plant. These are all mechanical systems. They have like their properties is that they have certain types of connections, and they have liquid or air flowing through different parts or components, which does not exist in electronic systems. And on the other side, we have electronic systems which have components and they have connections that are basically electronic connections. It can be like radar, it can be sonar, it can be any types of electronic system that you can think of. So usually when, especially in the military, when they talk about training troubleshooting, they mean either or both. They call it electromechanical troubleshooting. And so according to the belief in near transfer, in each of these tasks, in troubleshooting, for example, a specific type of vehicle or Humvee, you should just get trained on that specific system. Or if there's an electronic system, you get trained on that specific system, radar, for example. But the belief in far transfer goes beyond that and says that, again, as I said, in near transfer troubleshooting, each system should have its own training simulator, but if we can derive the shared characteristics of these systems and the troubleshooting task, then we can train that regardless of the system. And it is something like training general troubleshooting. So those training scientists came and said, well, there are a lot of similarities between troubleshooting in each of these systems, whether electronic or mechanical. There are components, there are connections, and basically they are the similar tasks. What if we teach just this general troubleshooting skill that can be transferred to all of the systems? So they try to find the similarities between troubleshooting tasks. And of course, in those troubleshooting tasks, in all troubleshooting tasks, there are components in each system. Now, the component might be the carburetor in a automobile engine, or it might be a certain circuit or sub-circuit in an electronic system. So it has different level of granularity, but it's basically the same component. And these components are connected to each other, and there is a connection. Now, there might be direction to that connection or not, but basically, connection is connection. And there is an output to each system, and we observe the output And we see that, for example, there is a fault. And then from that output and from that fault, we try to find the faulty internal component. So it's kind of a diagnostic process that's, again, shared in all troubleshooting tasks. And then, again, you trace it back to the faulty component. You find and replace the faulty component. You repeat, and you see if it's working. And this kind of loop continues until you find the faulty component. So this is kind of abstracting away the troubleshooting task in all systems, in electronic systems and mechanical systems, in each specific troubleshooting task. And if you can train this abstract skill, then that person or that operator might possess some skills or might develop skills or what is called as general troubleshooting skills. Then after that, with just some basic knowledge about a system, that person will be able to troubleshoot that system. So that was the notion behind the introduction of general maintenance and troubleshooting programs in the military. That still continues even today, and it's very crucial for US military. So that kind of abstracted away types of tasks or skill is something that cannot be trained with a high fidelity simulator because we do not have a system and its details. We just have an abstracted away set of instructions that we need to train. There is no details. There are no environmental details so that we can replicate them in a realistic way. And so this idea necessarily needs low fidelity systems because it's basically components and connections that can be drawn on any piece of paper. So if you think about it, I'll talk about this example in the next session. But if you think about, for example, each of these circles are components in a system, and these lines are the connections between those components. And that can be considered as a very simple low fidelity training simulator for either an electronic or mechanical system, like general. And then on this side, you see a higher fidelity simulator for training, but it's specific to a system. It's limited to a system. This one is general purpose troubleshooting. This one is a specific troubleshooting of specific system. And it needs the knowledge of that system, the goal of the system, the properties of the system, and all of the other details. So you see on two sides, very low fidelity, and the other side, high fidelity simulator. So if you think about using this low fidelity simulator, can you think about like the benefits of using this idea of abstracting away the basic instructions or basic components of the skill and teaching them with or training them with a low fidelity simulator? Can you think about the benefits of this? Yes. It trains a lot more at once than using specific simulators for system. Yes. Any other? Yes.
Chris, and it's probably a lot easier to change the task that needs to be completed. scenario versus actual computer simulation. And if you want to change the task that the trainee has to complete in computer simulation, that requires hours of going through code, debugging, a lot of stuff. And this is just simply changing the layout.
Yes, exactly. You can easily change the task without, in a very cheap way. I mean, you don't have to change anything in the simulation or in the training system because there is no training system. It's basically a very simple drawing or 2D simulation that can easily be changed. Yes?
My name is Mark, and the other one is kind of because like with it takes a lot of time first of all because they really just like to do the morning. So it can save a lot of time.
Yes, it can save a lot of time and resources. Of course, higher fidelity simulators are more expensive to develop and maintain, but low fidelity simulators simple to expand and maintain. Yes.
My name is William. I was about to say that you can do it in a wide variety of locations. So you might only have Android simulators, technology,
Yes. If you think about those cases that we talked about, like SimNet, like those high fidelity simulators, they were very localized in training centers, difficult to move or have or expand or transport to anywhere that you want. But this one, it's basically just some components and it can be basically transferred anywhere with some pieces of paper or some 2D plane. Yes.
I would say increase efficiency. If you have more general training time, more general manpower, you don't have just conjugate now.
Yes, exactly. And this one is very important because the kind of skill that you develop, it's called, it increases the efficiency of training because the kind of skills that you learn is not limited to a specific system, but it can be shared among a lot of systems or many systems. Or if you think about, like, say in the military, they can do a research and say that these are the similarities or similar aspects of our systems, and we abstract it away, we put it in such a simple form, and then we train them. That's it. It increases the efficiency. You no longer have to spend a lot of time on each of those systems and training them. The end result, you might argue, the end result exactly applied to the real world? The answer would be probably not. They still need a bit like real world experience, but the basic training that they get or the basic skill that they develop, it makes it much easier for them to go to the real world and do real troubleshooting tests. So it's very efficient to train in this way.
My name is Alex. This is a question. What would be like the kind of format for like a low fidelity simulator? Is it like a lecture or video structure? What's the kind of format? High fidelity.
Yeah. So this is specific one. This can be on piece of paper, basically. So you have this, for example, and this is something like they give you this as a board, and this is the output. And they say 0 in the output means faulty, or it should be 1. Now find the faulty component. And you do certain steps to find the faulty component, for example. That's a practice. It can be conducted on any piece of paper or any 2D plane or just a computer screen, for example. But if you think about other examples of low fidelity simulator, like those used in surgery or others, they use like simple materials, like things like cups or tubes or simple or like pieces of wood or simple materials just to replicate that experience of using different tools. So it depends on the task, but its its material is basically much simpler than high fidelity simulators. It no longer needs necessarily the presence of computer. Yes. And I'm just thinking about other examples of low fidelity. We will talk about that in the next session, about the specific cases of low fidelity simulators. Any other? Yes.
Michael, is the difference between low fidelity and high fidelity subjective, or is that hard to know?
It can be defined. I mean, it is usually when we talk about low fidelity versus high fidelity, it is the level of similarity of that material to the target environment. So it can be measured objectively very often. It can be measured objectively. And but subjective, it gets more complicated because you can have simpler tasks, but the psychological processes is basically very close, just like what we talked about in the mental space and the physical space. So if it is also far away psychologically, then it means that there's something wrong in the training that is not replicating that same experience. But it's a good question. It's often objective. Any other question? Okay, so I mean, all of those cases that you mentioned were accurate, but just just to focus on two main reasons or two different factors or benefits of using low fidelity simulator is first is increasing speed in training. You no longer have to spend time on each system, instead speed and efficiency, of course. And the second one is the generalizability of the skills that are acquired. So you can basically claim after training with that kind of material that now I have a skill in troubleshooting. What kind of troubleshooting? Any kind of troubleshooting. Electronic or mechanical systems. So your skill is more generalized or generalizable. These are two key benefits of using low fidelity simulators. Yes.
So, just I have a question that whether all skills are generalizable to the same like task. I mean, like, well, say 5 different tasks are generalized to 5 different abstract tasks. And I mean, that they are not in, like, how can we abstract them? Yeah, you know.
So we have 5 different tasks.
Yeah. And like, I mean, you know, like for apartment where you're trying to find somewhere.
Yes.
But is that, so you have to have 5 in mind at the start, and then you develop.
Well, I would say that it comes from detecting the similarities between tasks. So if there are like 5 random tasks that come out of nowhere, and we do not find similarities between them, it's difficult to come up with a simple, like, derived aspects or shared aspects of those tasks. And so, yeah, it makes it difficult. But when you are in that like business and you say, well, I think there is a similarity between this, and this task, and I can abstract away those shared aspects, then yeah, you can definitely do that. But it does not start with selecting 5 random tasks. So just as your example, if we have 3 different tasks, task number 1, 2, and 3, and we say, well, I think I can find a similarity between them. They are similar, like those examples of electronic and mechanical troubleshooting. And then we find their isomorph, or their shared form, or shared aspect, just like those things that we counted for troubleshooting, like there are components in each circuit or system. There are connections between components. So these are all shared in all types of systems. And we can like find these shared aspects are called the isomorph of that problem that is shared in all of these tasks. And of course, the next step is after we develop this isomorph, we train that isomorph. And training that isomorph develops a skill. And it is important to remember that this skill can be generalized to all of these tasks again. So that's the basic idea. Yes.
What are the arrows that are going back up?
So it's basically the skills that are developed can be used to train those original tasks. Or one might argue even other similar tasks in the same domain. Another name for this problem, isomorphism, especially in psychology literature, it is also known as analogical reasoning. So you find an analogy or similarity between different systems or tasks, and people, as they say, reason in the same way. So, or find this analogy between the different tasks. So if you have a vehicle like this with 3 wheels and you drive it, in a different task, you have driving of an automobile, and in a different task, you have driving of a truck, of a large truck. Then the question would be, well, can we train these tasks with one simulator? And to do so, we have to derive the shared aspects of those tasks, whatever is shared between them. They all have wheels, for example. They all have, like, you can turn the wheel and experience certain things, for example. They have brake, they have gas pedal, for example. These are shared aspects, and we derive these shared aspects in a simulator, and we try to teach it or train it that way. So this is basically the kind of mindset that you can have in mind. Usually it's used for low fidelity simulators, but in this case, this particular case, you can also come up with a comparable like mid fidelity, because you cannot get close to each of these systems. Then it becomes a specific simulator. But you want to train a generalizable skill, so you don't have to, you cannot be as high fidelity as you are in like specific simulators for truck driving or automobile driving. So it's basically trying to abstract away the basic essential shared components of these tasks and train it so that the skill can be generalizable to all of these types of vehicles. So as we mentioned several times, the belief in near transfer focuses more on the human side, human activity, psychological activity of each task instead of the physical properties of systems. So if you want to see that there are similarities between different tasks, look at how humans are conducting them. And if you see that, oh, is basically similar between these two tasks that look different on the surface, then you might be able to find those or to derive those similarities, create a training system for both of them. So the same thing.